All right, I clicked on recording on my side.
Okay, awesome.
All right. Okay.
I just want to be able to have a copy of this because sometimes I forget what happened where and certain steps and you know.
Sure. Can you see the screen?
Yes, sir.
Okay. Let me know when you're ready and we'll start.
I'm ready to go.
Okay. Uh, so stop me anytime we go over something or I go over something too fast and you don't understand it, okay? So
Sounds
again,
good.
I'm gonna pretend that I'm in the exam room and I'm gonna do this at full speed that I normally would, but I'll
Mhm.
announce everything that I'm doing, everything that I'm thinking as it comes to my mind, okay?
Okay.
All right, here we go. Number one says, draw the circuit for a simple 1 to 2 binary decoder with an enable using and or an inverter gates. Okay, so it says we're drawing a simple 1 to 2 binary decoder. And then I remember, what does a binary decoder normally look like? Its job is to make it so that, let's actually draw a truth table for that real quick. So the input is W naught, the two outputs are Y1 and Y0. So that obviously with a single bit, you can either have an input combination of 0 or 1. So the idea behind a decoder is W naught tells you which of the outputs should be asserted. So in this case, I see W naught is 0. So it's Y0 that should be asserted. Everything else should be 0. In the second case, it's telling you that it wants Y1 to be asserted. And when I say asserted, it means make it a 1. Everything else should be 0. So the decoder is 1 hot. What that means is in each of these rows, you'll notice that only one output is high at any given time. So now I just reminded myself what a decoder is. Now I
Mhm.
know I have a truth table describing the relationship between the inputs and the outputs, so I should be able to easily build this. The only thing is it says that we should also have an enable input. So let's add that real quick. So the idea is if the decoder is enabled, then it will operate in the exact relationship that we just described. If it's disabled, as in if enable is equal to 0, then we don't care what W naught is. We're just going to make both outputs 0. So this is the disabled state. Make sense?
Okay, that makes sense.
Good. So we're going to build this circuit now. And I'm going to start by building this simpler circuit that we started with for just the decoder. And I can see the relationship very easily. So if I want to generate an expression for Y1, I can see that Y1 is exactly equal to what W naught. If I want to generate an expression for Y naught, I see that Y naught is equal to the inverted version of W naught. And then now I've got these intermediate signals here. And I can generate those pretty easily. So I'm going to call this Y naught. I'm going to put a little prime here just to know that this isn't what we're actually going to send to the output because we haven't taken into account this input enable yet. But for now, I'm going to generate Y1 prime and Y naught prime. So I see that Y1 prime is equal to whatever W naught is. So that's Y1 prime. Actually, I'm just going to flip the order around so that it's a little closer. I'm going to generate Y naught prime first. So Y naught prime is the inverted version of W naught according to this equation here. And then I can see that Y1 prime is equal to W naught itself. So there's Y1 prime. And then now if I want to take into account this enable, well, I can see that if enable is equal to 0, then I want both outputs to be set equal to 0. I can do that by adding an AND gate in front of each of these. So that will wire up to there, that will wire up there, and then the enable goes into each of these AND gates. The idea behind this is if enable is equal to 1, then whatever Y naught prime is will make it to the other side because it'll be ANDed with a 1. So Y naught prime ANDed with 1 is still Y naught prime. Same thing down here with the Y1 prime. However, if enable is equal to 0, it forces these outputs to be 0 because anytime you AND anything with a 0, the output of the AND gate is going to be 0. Make sense?
Right.
All right, so we're done with question 1. Do you agree with everything I've done?
Yep, makes sense.
Any questions?
Well, I don't think so. Number one, I thought number one wasn't as bad compared to the rest.
Okay. Okay. Let me know, by the way, when we get to a question that I should put a little more emphasis on, and if I should go faster on certain ones that you find easy. Okay.
Gotcha. We'll do. Thank you, Richard.
All right. So now we're on question 2. Question 2 says a 2 to 4 decoder has an input valuation of W1 equal to 1 and W naught equal to 0. So this is a 2 to 4 decoder. So it's similar to what we did up here with the 1 to 2 decoder. A 2 to 4 decoder is no different. It just has 2 inputs this time. and 4 outputs, y3, y2, y1, y0. So with 2 inputs, you can have a total of 4 different combinations. In decimal, this one is 0. In decimal, that's a 1, that's a 2, that's a 3. And again, the input is specifying which of the outputs should be high. So in the first row, it's telling you that y not, that output should be high. In the second row, it's saying that y1 should be high. In the third row, it's saying that y2 should be high. In the final row, it's saying that y3 should be high. Again, the input specifies which of the outputs should be asserted. So then everything else must be a 0, because again, decoders are 1 hot, meaning that only one output is asserted at any given time. So in this case, it's saying, what if W1, W0 is equal to 1, 0? Well, that hits this case here. And then just like that, we have our answer. We have 0, 1, 0, 0. Does that make sense?
Yeah, that makes sense.
Okay. Any questions?
No, not yet.
Okay. Good. Question 3 says use a single 4-to-1 mux and any other non-mux gates to implement the following 3 input. Let's actually move this off to the side so it's not bothering us. So this one says use any other non-mux gates to implement the following 3 input truth table. Use x and y as the select variable on the mux. So it says put x and y here. So let's do that right away. And then it says draw the circuit and label the inputs and output. Use the truth table directly, the graphical method. Okay, so this is saying the output of this mux will be equal to f. So we're relating this truth table to the picture that we see on the screen. And so now let's ask ourselves, well, what should f be when xy is equal to 0, 0? So we go into this table and we see where is xy equal to 0, 0? Well, in these first 2 rows, xy is equal to 0, 0. And we can see that the output is always going to be 1. Doesn't matter what z is. When xy is equal to 0, 0, the output's going to be 1. Do you see that?
Mm-hmm.
So that's why I'm going to hook up a 1 right here. And then I call it a day. And now the next thing we're going to focus on is instead of the 0, 0 case, instead of the 0, 0 case, we're going to look at 0, 1. We're focused here now. So we highlight all the locations where the table is equal to 0, 1. And we can see in this case, the output f is the inversion of whatever z is equal to. So it should be not z that goes into there. And then we move on to the next one, which is 1, 0. And we see that 1, 0 is over here. And then again, in these 2 rows, we relate the left side of the table to the right side, i.e. the inputs with the outputs. And we see in this case, f is just equal to z. So here we just wire up a z. And then in the final row, same thing. We focus on where xy is equal to 1, 1. And that's here and here. And we can see in this case, f is always 0. It doesn't matter what z is. So that's why over here, I'm just going to hook up a 0. And so we're almost done. This had to draw out the circuit. So instead of saying z bar and z, let's actually make these little labels here just to remind us. But here are the actual inputs, x, y, and z. So x goes here, y goes into that wire, and then z goes through an inverter. And this inverter will go into z bar. And then the regular version of z will go there. And then we're done. Do you agree?
Right, that makes sense.
Any questions?
I don't think so far. It's making
Okay.
a lot of sense, but I guess I have a slight question. Could you also do that? I mean, could you just do this with so it says like the graphical method. Does that mean like not using Shannon's or?
Yep, that means not using Shannon's.
Okay.
Graphical is what we just did.
Okay, so just using the truth table.
Yep.
Okay.
Yep. I think there was another one that asked about Shannon. So you'll see us through Shannon's down there.
Gotcha.
How's the speed? Am I going too fast or is it okay?
Perfect.
Okay. Next question says draw a gated SR latch. So when I see this on the exam, I'm going to remind myself, what is an SR latch? S stands for set, R stands for reset. So here's the symbol for an SR latch. The 2 inputs are S and R. The output is Q. There's usually an enable as well, which we denote as CLK. So whenever clock is high, that's saying that this latch is enabled. But this is a symbol for an SR latch. So actually they drew it down here for us already. So I redrew it. Notice that they had a Q bar here. So I'm just going to ignore that. Q bar obviously will just be whatever the inversion of Q is. So I'm going to keep it simple. I'm just going to have a Q here. Anyway, what set means is make Q equal to 1. Reset means make Q equal to 0. That's by definition what set and reset means. Set means to make it a 1. Reset means to make it a 0. So just like that, we know what this is supposed to do. Let's write out a truth table now, because that's what actually matters to us. So we ignore the clock. We know that the clock is just acting like an enable, so we don't have to put it in the truth table. Let's just look at SR and what their effects are on Q. So again, with 2 inputs, we know that we can have a total of 4 input combinations. So let's ignore this. We're going to ignore the first one for now. We're also going to ignore the last one. We're going to focus on this row. This is saying that we don't want to set Q, but we do want to reset Q, meaning that we want to make Q a 0. Again, I'm just going off of these definitions here. So if R is equal to 1, it means we want to make Q 0. So in this case down here, S is equal to 1. So it means we want to make Q equal to 1. So there's the 1. And then this one up here, so we're going to ignore the bottom case for now. So the very top case here is saying we're not going to try to make Q a 1. We're also not going to try to make Q a 0. So really this is kind of the lazy state. It's saying do nothing. So 0, 0 means we're not trying to make it a 1. We're also not trying to make it 0. So basically we're not trying to do anything to it. And so that's called the memory state. So Q is whatever it previously was because we're not changing it. And so this is the latch state. This is why we call it a latch. We're neither trying to change the value to make it a 1 or a 0. We just keep it the same. And then this one down here is the state that we want to avoid, because this one here is the bad state. So we're not even going to try to say what Q is equal to there. The idea is this is saying we want to make Q a 1 and we want to make Q a 0. So in reality, you don't want to do that because you would be shorting. If you try to drive 5 volts on a wire and drive it to a 0 at the same time, you would be shorting the circuit, and that would not be good. So this is a state that you want to avoid. So in the later part of this exam, practice exam, there's a question that goes over a JK latch, which is basically an SR latch, but designed so that we avoid this state. But for now, does the top 3 rows, do those make sense to you in terms of set and reset and their definitions?
That makes perfect sense.
Good. So looking over here, it's asking us to draw a gated SR latch using NANDs. So this is very easy to do. So we're going to ignore the word gated for now. Gated again just means that we have this clock input here to make it enabled or not enabled. But for now, NANDs or NORs, so you can build SR latches using either NAND gates or NORs. But with NAND gates or for NOR gates, they look exactly the same, except the body of the gate would look a little different, the shape. But we do a cross coupling, and so the output of one gate goes to the input of the other gate. And then same thing up here. So the input of the bottom gate is driven by the output of the top gate. And then here's the S input that goes into there. Here's the R input that goes into there. And there's your Q output, there's your Q bar. This is something that they probably showed you in class. Maybe they built it using NOR gates, but the architecture is the exact same. It's just that instead of drawing the shape that looks like this, you curve this and you call it a NOR gate. Does this picture look familiar to you for an SR latch?
Yeah,
Okay.
it looks familiar. I just have a question about how the clock relates to it, though.
Sure. So we haven't gotten to the clock yet, but the clock is what gates this latch. So let's go over the clock now. So again, we just went over the basic SR latch. So now let's talk about the clock. Ignore this for now. So now we include the clock, which again is like an enable. So instead, I'm going to say clock/enable. So the idea is when the enable or the clock is high, then we want the SR latch to operate the way that we described it to work earlier. So we don't have to change anything about the truth table. But if the clock is disabled, then we don't care what S or R is. We want to force Q to be 0. Or actually, it would be better to keep it at the previous state. So as a designer, you get to choose what happens when you gate or if you disable the latch. So with a latch, if you disable it, it would be a good idea to make it so that the Q output is always just whatever it previously was, and it can't change. Do you think that's a good design decision?
Wait, sorry, repeat the question.
Okay, question is from a design perspective, does it make sense to say that the output of the SR latch will just retain its previous value if we disable it, if we gate it, meaning we make the clock signal or the enable signal, if we set that to a 0, would it make sense that we would want the Q output to not change?
Right, yeah.
Good. So if disabled, don't change. If disabled, don't change. So it retains its previous value. Make sense?
And yeah, and then if the clock's on and S and R just equal to 0, then it's the same. You just stay in the previous state too, right?
Yep, exactly. So there are two ways to get the previous, to retain the previous value. It's way one is to disable a clock. Way two is to enable a clock, but set SR equal to 0, exactly. And then again, our design decision is to make it so that if we're disabling the latch, then we make it so that Q does not change. It just retains its previous value. Does that sound about right too?
Yeah, that makes perfect sense.
Good. So we come here and we see that, oh, well, if we want to implement this, I think you were on the right track. You said, oh, well, if we want Q previous, we just have to make it so that S and R are both set equal to 0. So what we want to do is we want to see if we can hijack this path. So again, right now in this circuit, we have S going directly to the AND gate, the R going directly to the bottom AND gate. We want to hijack those paths now. And when I say hijack them, I literally mean instead of, the idea is the clock based on the value of clock. If it's 1, then we'll allow whatever these inputs are to go to these AND gates. But if clock is equal to 0, we want to hijack those paths and we want to force them to be zeros so that we kind of force our way into this first row up here. Basically, again, if the clock is 0, we want Q to be the previous state. And then we know we can get Q to be in the previous state if S and R are equal to 0. So we're going to hijack this path and make it so that the input to the top is 0 and the bottom is also 0, making it so that we retain our previous state. Does that make sense?
That makes sense.
Okay, so let's hijack the path. So let's erase the paths and then let's hijack them. So the idea again is if the clock is equal to 0, we want the inputs to both of these gates. Oops, I didn't want to erase it. We want the inputs to both of those NAND gates to be 0. So we can use we can do that pretty simply, just like we did earlier with the other enable question that we had, again with an AND gate. So S goes into one of them, R goes into one of them, and then the clock goes into one of them, and then the clock also goes into the other one. So again, just like earlier for the very first question up here, we had an enable. And in the way that we took the enable into account was we placed AND gates in series. So that's what we're doing here. So these, sorry, I meant to say with respect to the Y naught path, we put an AND gate in series in there. Same thing with the Y1 path. We inserted an AND gate in between that path, which was originally Y1 prime and Y1. So coming back down here, we insert these AND gates in here. And what that'll do is, again, if clock is 0, it'll force both of these outputs of those AND gates to be 0, making it so that the output of these two NAND gates will retain their previous value. Does that make sense?
Yeah, that makes perfect sense.
Any questions?
So in terms of, so like the question wants it in NANDs. So would you just need to just convert it into a NAND after that, and then that's it?
Oh, I see. So yeah, so these are NANDs, and you're pointing out that these are AND gates.
Yeah.
Right. Okay. So we can convert those to NANDs. It's not hard for us to do. Ultimately, this is an AND gate, right? And if we want to convert it to a NAND gate, it looks like this. But we do want that AND capability, so we want to send it through an inverter. So this inverter here, you can actually implement using another NAND gate, right? So with a NAND gate, we recall what the truth table is real quick. So A, B, and an A and B not. So 0, 0, 0, 1, 1, 0, 1, 1. And the output in each of these, this one would normally be 0, but it would become 1. That would normally be 0, becomes 1, 1, 0, like that. So we want to use a NAND gate as an inverter. And what we can see is we can get some inverter looking action right here. See that? See how the output is the inversion of whatever B is?
Right.
Okay, so what that's telling us is, say that this is input A here's B, and by the way, this is an AND gate, a NAND gate. So what it's saying is let's tie A to 1. So let's tie this to a 1, and then whatever B is will come out, and you'll get B bar. So that's how you create an inverter using a NAND gate. Make sense?
Yeah, that makes sense.
Okay, so really, what we can do, I'm not gonna redraw this picture up here. I'm gonna get rid of these zeros though, so we don't think that they're bubbles. So we get rid of those zeros. And then down here, what we're gonna do is we're just gonna say, oh, by the way, an AND gate, so that's the AND gate. It's equivalent to 2 NAND gates that look like this, where this one is tied to a 1. So there's your A, there's your B, there's your C, there's your A, there's your B, there's your C. So now you have your AND gates in terms of 2 NAND gates. Is that fair?
That makes sense.
So you would just substitute those into there at the top and here at the bottom. And then we're all done with this question. Do you agree?
Wait, I have one question. Where does the, okay, so where would the 1 come from?
This one here. So when you design a circuit, you usually have access to about 5 volts. Have you ever breadboarded before?
Yeah.
Okay, so the plus 5 volts, you might get that from a power supply. And if you ever look at what one of these 74 series chips from Texas Instruments, have you ever played with those integrated circuits? They're usually 8 legs that come out of it.
Yeah.
And so one of these legs will correspond to this input of this NAND gate, and you're literally going to tie that to 5 volts. You're going to take a wire between that leg, and you're going to plug it.
VCC and for the input.
Yep, exactly. So this input to this particular NAND gate, you're going to take a wire and hook it up to the red rail, which is VCC or 5 volts.
Okay, that makes sense.
Good. So the idea is in circuits, with circuits, you always have access to constants, 1s and 0s. Those are literally your rails. And so you just take a wire and you connect it to the rail, or the plus, the VCC and ground. Good.
Right, that makes sense. I think in class we did all the NOR and NAND conversions on our last exam, but we had like some other method where we like put 2 inverters, like for if it was like NAND, we put like an inverter after the and then like a bubble on it, and then like if there was a NOR, then we put like an inverter before it and like 2 bubbles, sort of.
Okay, I think that we're gonna see an example like that down here where it says to convert everything to just NAND gates. Let me see if I can find it. Maybe it's not in here. I thought I saw it earlier though. It gave you a circuit and I told you to convert it into a bunch of AND gates. But actually, yeah, this was probably it. But we can go over an example of that at the end. How's that sound? Where we do so you're talking about bubble pushing. So let's just write that off to the side. Let's come back to bubble pushing later. But any questions on that last question we just did?
No, I think you did a great job explaining it.
Very good. All right, let's go to the next question. This one says, complete the following schematic, number 5, to create a positive edge triggered flip-flop. So these are both D latches. The difference between a latch and a flip-flop in terms of the way that it looks, I'm gonna give you a simplified version real quick. So this is a D cube flip-flop I'm drawing, and that little triangle symbol at the top, that tells you that this is that's your clock input, but the triangle means that it's edge triggered. And that means that it's a flip-flop. And then the other picture that you might get looks like this. D, Q, and you might see them write CLK here, or they might even write enable here. But the idea is this here, since you don't see the triangle symbol, so the discriminator is a triangle. If you see a triangle, it means it's a flip-flop. If you don't see a triangle, it means it's a latch. In terms of the way that we draw these pictures, triangle means flip-flop, no triangle means it's a latch. So coming back here, these are both latches because there are no triangles. So it's saying with these 2 D latches, because these are D latches, or sometimes you might call them DQ latches, but you have 2 of them. How do you use them to generate a regular flip-flop? Well, this is a very basic thing. Like you kind of either know it or you don't, and I'll explain it to you at the end. But this is something that they definitely would have taught you in class. And what we'll do is it says positive edge triggered. So what we want is we want it so that this latch here is able to change when the clock is positive. So we want the positive version of the clock to go here, and we want the inverted version of the clock to go here. And then D will go into there. The output Q or the first latch will become the D input of the second latch. And then these are your answers, Q and Q bar. Have you seen this before? Do you want me to explain why this is the case?
Yeah. I mean, we've gone over a lot of this stuff in class, but the problem is, it's like it's a 150-person lecture, and nobody really seems to know what's going on until like right before the exam. So it's
Okay.
just kind of like
No
a
problem.
little hectic.
So let me explain it. And the way I'm going to explain it is by simulating it. So this program is called Logisim. I would recommend downloading it if you don't have it. You can simulate your gates in here. So let me grab two latches. So I know that it says the flip-flop, and I know it has a triangle. But in this program, they don't have regular latches. At least they don't have the symbol where it doesn't have the triangle. So just ignore the triangle. I explained earlier that on this exam, triangle means that it's a flip-flop, no triangle means it's a latch. In this program, you'll see that they always have triangles, so just ignore that here. But right now, they're both latches. That's all you need to know. It's a DQ latch for both of them. And then let me explain how a latch works first. So here's your input. Here's the input D, and then here's the output Q. And you're gonna look at the color of the wire. See how right now it's dark green? So what happens is if I turn it on, it becomes light green. See that?
Mhm.
Okay, so now here's the clock. And then what you see is, see how the input is green, light green, but the output is, so basically input is a 1, output is a 0. So the output does not see the input until the clock or the enable is high. So now
like
it's
what we just did, right?
exactly.
Clock is enable.
Yep, exactly. The clock is an enable. So think of this as a blind or like a window or like a door to your home. Unless if the door is open. So this is the person that's outside, and this is you on the inside looking, and you can see the person outside. You see that they're sending a 1, it comes inside your house. Now, if you close your door, then what happens is if the person outside does other stuff, you can't see him anymore. You just see the last thing that they did, which was they sent a 1. See that? So that this stays here. That's what a
So, like,
latch does.
the memory retention is based on the clock, right?
Exactly. So the idea is when the clock, or in this case the enable, when it's 0, then the output retains the previous value. Exactly. And so what we do is we think about this and we say, oh well, what if we put 2 of these back to back, right? So let me delete this real quick. So here's another latch, and it behaves the exact same way as what you just saw here. So any questions on the behavior of the regular latch so far, by the way?
No, that makes perfect sense.
Good. So now let's disconnect this real quick. There's the output. Now let's put 2 latches back to back. And let's take the Q output of the first latch. So I can think of these as doors to your home. So this is the front door to your home. And then say that this is like there's a hallway now and there's another door. And now say that you're standing here. And now here's that Q input going into the D input of the second latch. And then this is you. The output is your eye and what you can see. So what we're going to do is for now. Are you saying something?
No, I didn't say anything.
Okay, it's just your audio got very loud for a second. Say something again.
Hello, check.
Okay, good. All right,
About
can
that.
you?
What happened?
All right, you can still hear me fine, right?
Yeah, you're fine.
Okay, good. So watch this. If I were to just take the clock signal, let me give these names by the way so that you can see. So there's the clock, and then this is the outside world. We'll call it stimulus or external. So what you'll see is if I were to wire this clock over here like this, it becomes kind of useless. It's kind of like both doors are open at the same time. See how I changed this? See how if both doors are open at the same time, you can see what the person outside your house is doing. So again, this is the front door to your home. And then between the front door and your actual home, there's a hallway, which is this section in here, in between these 2 latches. And then this is the door, this is the actual door. This is the hallway door. And then beyond that, that's where you're standing. So you can see that if both doors are open, meaning that they're both enabled, both latches are enabled, you can see all the way out to the output. See that?
Right. Which
If
shouldn't
this
be the
person, yep, if this person's outside dancing around, you can see him. But now what if we make it so that only one door can be open at a time? Meaning, let me disconnect this door, for example. let me put a NOT gate in here. So what this is going to do, what this setup's going to do, is it always ensures that one door is open and one door is closed because we've got the inverter, right?
Right.
So now watch what happens. Right now, it's the second door that's open. You see how the green wire makes it all the way here? Whereas in front of this one, the enable, since it goes through the inverter, see it's off. So the front door is closed, but the hallway door is open. So what that means is the person outside can dance around as much as they want. The person, you won't be able to see it because they were not able to, this person that's outside, they didn't make it through the front door. But now what happens is, watch this. If I were to toggle the clock real quick, now the front door is open, but the hallway door is closed. So now that person that was outside the front door, the people in the hallway can see them, right? So see how the hallway now lit up in light green. So now what happens is, watch, I'm gonna disable I'm gonna click on the clock again. Now the people see this wire that was the D input of the second latch, that makes it all the way to the output now. Again, it's kind of like the reason why we call it a flip-flop is because only one door, there are two doors, only one is open at any given time. So they flip-flop, flip-flop, flip-flop. And the idea now is the person outside, again, can dance as much as they want. Front door is closed, so they can't see the person dancing around. But they do remember that the last value that this person was a 1. So that stays there, because again, the door is closed. So that value stays, it's latched. Make sense?
Right. That makes sense.
Okay, so the reason why we call this a flip-flop, let me explain flip-flop real quick. Here's the flip-flop. So again, this is the simplified version of this picture up here. So these are 2 D latches that you see up here. That's a D latch, and the one on the right is also a D latch. The one on the bottom is a DQ flip-flop or a D flip-flop. The symbols look the same just because the way that this program works, but I've got them configured. So at the bottom one is a D flip-flop. Change that name real quick. So this is a D flop or a D flip-flop. And so you'll see that they work the exact same. So let me drag these 2 inputs out a little bit for room, and watch. Here's that external wire going into the D input. Here's the clock signal going into the flip-flop. Here's the output. What we want to see is that the output for the circuit on the top and the circuit on the bottom are the exact same. That'll confirm to us that we've designed it correctly. So watch this. For now, let's disable the clock. Let's get that ready. So right now, see how the output's a 1 in both cases? Okay, now let's play with this. Output remains a 1, so that's good. Let's turn off the clock. Let's play with this. Output still remains a 1. Now let's turn on the clock. Both of them became zeros just now. Let's play around with that some more. The clock, nothing changes. So it looks pretty good, right? Top circuit looks like it behaves the same as the bottom circuit, right? Are you thinking, or did we lose connection?
No. Oh, I thought you're moving on. Sorry.
This is
I have a question about the D latches.
sure.
So how does that relate to the SR latches?
So the SR latches can be you can build a D latch from an SR latch is the answer. So let's come back to that at the end. Okay. So we have a little bank of questions here. So we have bubble pushing, and then we have going from SR latch to D latch, because there's another question at the very bottom of this exam that's similar, and I think that'll be a good place to touch on this. Sound good?
Okay.
So we're gonna parking lot that for now, but for now I just want to quickly explain to you. Well, first, I think you agree that the top circuit with 2 D latches, we can build a D flip-flop. Do you agree?
Right.
Okay. And then I'm going to explain what a D flip-flop is, but also take a visual picture of this for now. Actually, let me just snapshot this and put this into our whiteboard, which is here. Okay. There it is. Let's put it there so that you remember what it looks like. And then coming back here, I want to give you the physical explanation of the flip-flop now. So ignore this stuff from up here. Like with 2 doors, you're able to build a flip-flop is the idea, i.e. 2 latches, you can build a flip-flop. But really what the purpose of the flip-flop is, it's, have you ever heard of sample and hold before in your electronics classes?
I don't think so.
Okay, so the idea is again, this is the external stimulus. And so the way that the flip-flop works is on the rising edge of the clock, we sample, and only when this transitions. Rising edge means the clock transitions from low to high. So when the clock transitions from low to high, Q samples, it copies whatever the external input is, or the D. Let me just change that to D for now, so it matches the name of the input to this device. So we call it a D. So the idea is on the rising edge of the clock, Q copies whatever D is. So watch this. D right now is 1. Now if I give it a rising edge on the clock, see how that value on D got copied onto Q?
Right.
But now D can do whatever it wants, but Q does not get affected. It's being held. So there's your hold, sample and hold. So the value is held, and then it's guaranteed to be held until the next rising edge of the clock. So now if I give it a rising edge, so right now clock is 0. If I click on it, it becomes 1, giving it a rising edge. So now you can see that the output changed. It's no longer green, it's dark green now, because again, it's sampled D onto Q. So we use D flip-flops to sample, to hold stuff. Make sense?
Yeah, that makes sense. So this one is based on the clock cycle.
Right. So the D flip-flop, I'm going to write it out. D flip-flop samples or copies, instead of, I'm going to say copies D onto Q when there is a rising edge in the clock signal, and that's it. So with the latch, the difference with the latch is it's the trigger isn't the rising edge. It's as long as the clock is high, D will get copied onto Q. So let's make that very clear.
So on the last one, clock was just the enable, but now it's based on the clock cycle, right?
The clock edge, say edge, the edge.
The clock edge.
So when the clock goes from low to high, then that's when D gets copied on the Q. So this is kind of like a lazier version, basically, of the latch. Right. So here's the latch again. I'm going to change that to logic high, and then here's the clock. Here's the D input. Here's the Q output. So the idea is, if you take a look at the top and the bottom, see how the top is working harder than the bottom, because the top, as long as clock is high, it'll copy D onto Q. But on the bottom, it only copies D onto Q when there's a low to high transition. Make sense?
Yeah, that makes perfect sense.
Good. So the D latch copies D onto Q when clock, also known as your enable, is high. So that's the difference between the latch and the flip-flop. And again, the flip-flop contains 2 latches inside of them, which are like those doors. I don't know if it was helpful, that analogy with the front door and hallway door, but the idea is one door is open at any time.
Perfect sense.
Okay. All right. I think we're all done here. Any questions?
That makes sense.
Okay.
So
That's good.
For the question, you're just putting together 2 D latches.
Yep,
But
those 2 D latches, and only one can be open. One door is open at any given time.
Okay, that makes sense.
And then
You said we go over like the logic between a D latch and a SR latch at the end.
Yep, we will definitely do that. I'm going to show you how to go from SR latch to a D latch. Now let's put this here so that you have it too. And then just one last comment I want to make here. Notice that they said it's a positive edge triggered flip-flop. So that, remember how I was describing a low to high transition? It's only on the low to high transition. So when there's a rising edge in the clock signal, that's the same thing as a positive edge triggered flip-flop. Sometimes you might make it so that you have a negative edge triggered flip-flop, meaning that it only D gets copied onto Q only when there's a falling edge, when the clock goes from high to low. So if you want that, all you do is you flip the location of where this inverter is. So again, this right here right now is a positive edge triggered flip-flop. What that means is, again, on the rising edge of the clock, that's when the Q has an opportunity to change. If you want to switch it up a little bit, if you want to make it a negative edge triggered device, what you'll do is you'll put the inverter on this one.
Right, that makes sense.
Good. All right, let's back this up. Go back to the original answer. All right, are we good? Should we move on?
Sounds good.
Okay, draw the diagram for D, excuse me, draw the diagram for a D flip-flop with a synchronous load using a single mux and 1 normal D flip-flop. So this says we want a synchronous load and we want to use a single mux and a normal D flip-flop. So here's the normal D flip-flop, which again you saw. And again, the key symbol that differentiates it from a latch is that it has a triangle. So let's draw on the triangle. There's the clock input. And then here's the D input. Here's the Q output. This is the normal D flip-flop. Do you agree?
Yep.
Okay, so now it says a synchronous load. Synchronous just means that Q can only change on the rising edge of the clock. That's what synchronous means. It means everything is synchronized to the clock. So Q only changes on rising edge of clock. That's all it means. We can come back to that later. It gives us a hint. So again, it wants us to be able to load. Load means to initialize Q with a value. So when you write code, when you create variables, you usually initialize them to a 0 or to a 1. That's what this is saying. We want to be able to load it. So it says to use a mux. That's the hint. So generally, if you want to load, in addition to saying that you want to load, you should also specify what the load value is. So here's the load value, and on the bottom, there's the load. And so it's saying, basically, here's the normal D flip-flop. Let's hijack the path. And it's telling you use a multiplexer to hijack the path. So here's the D input, there's the normal D input, and we want to hijack this path. So hijack it means we use those multiplexers from earlier, remember? Same thing. Well, actually, earlier we didn't use multiplexers. I think we used AND gates, but then in this case, it tells us specifically to use a mux. So normally, again, it's the D, whatever this input is, that'll come into the D input of the flip-flop here. So and then we'll use the load signal as a select line to this mux. And so if load is equal to 0, it means that we don't want to use the load value. So if load is equal to 0, the D input will make it to the other side of this mux, and that'll be used and copied onto Q on the next rising edge. You agree?
That makes sense. But if load is 1, then are you just sending 0 through? Is that?
If load is 1, then we want to load it with the value that you want to initialize it to. This is the initial value. So this is usually an input as well. So you can say, oh, I want to initialize it to a 0. So you put a 0 here, and then you're going to set load to 1. And then on the next rising edge, the Q will be forced to whatever the load value is. Make sense?
That makes sense.
All right, and then we're done with this question. Anything you want to ask about this?
No, not particularly, but I have I guess a question about the load value. So if the question doesn't specify like including the load value, like would it be appropriate to include it, or?
I think from a design perspective, yes.
Okay.
Like you could say that like normally like D flip-flops usually has a set input. There's usually a reset too. They don't give you the opportunity to load for just a flip-flop. For a register, you can load typically, but let me show you here real quick. So you see how when I hover over here's the flip-flop. When I hover over it, you see how it says that this input is the clear input. See how it says in that little yellow box, it says clear?
Yeah.
Okay, so that's kind of similar to the load, but in this case, it forces it to a 0. Clear means to make it a 0. If I look here, there's also a reset. Actually, hang on a second. Clear means to, when 1 pin state to 0, and if this one, it'll make it a 1. Okay, yeah, this says preset, not reset. Preset means to make it to a 1. So this one here, to load it, you assert either the clear or the preset. So again, as a designer, it's your choice. You could say if someone says load, then it means you force it to a 0. But generally, if you say load, it means you should actually have some value that you want to load into there. So I think using a little bit of common sense, we deduce that there's actually one other input, the value that you want to load into the flip-flop. Does that make sense?
That makes sense.
Good. Any other questions?
I don't think so on that one.
Good. Let's continue on. This one says create a state assigned table for the following state diagram, and given the following state assignment, okay, so A, B, and C, they give you the state assignments for. They tell you that 1, 1 is unused. So that's great. Let's go ahead and do this problem. So let's see. They say that A is 0, 0. So I'm going to write. So when I see a problem like this, I prefer to use the letters. So this is A. That's B. This is C. and this is unused. I'm reading from here. See that?
Yep.
Okay, and then idea is, oh, I see. Well, if we're currently in A, and this input is W, this is the input. If W is equal to 0, I see that we're supposed to go to B. So again, if W is equal to 0, we're supposed to go to B. So I'm ignoring the state encodings for now. I'm just writing in the letters because it'll be faster. And then similarly, if we're at A and the input is 1, then we follow this arrow. It brings us to C. So here there's a C. And then this one here, if we're in B and the input is a 0, so again, we're focused here now, and the input is a 0, then we go to A. So what I do is I put an A here. Okay, well, what if the input is a 1? Well, if the input is a 1, we follow the arrow that says 1 next to it. So it's this one here, so we go to C. So I put C here. Oops. I put a C there. And then the next one we're focused on is from C. So if we get a 0, we go to the B state. So here I put a B. But if we get a 1, we're also gonna go to the B state apparently. So from C, yeah, it always goes to B. We just traced all the arrows just now. And now what I'm gonna do is I'm just gonna copy this off to the side. And then I'm gonna fill in the actual values that should go into this table. So we know that B is 0, 1 because it says that right there. So there's the 0, 1. And then the next one was supposed to be a C, and I see a C is a 1, 0. So there's the 1, 0. Next one is the A. The A we can see is 0, 0 from here. So we say 0, 0 there. And then C we already knew was 1, 0. B we already knew was 0, 1. B we already knew was 0, 1. And then again, these were unused, so we can put X's here. We don't care. And let's see, the output. We can see this is a Moore machine. It's telling us that if the input is A, the output is going to be 0. That's what the A/0 means. So if the current state is A, the output is forced to 0. So PS, I think that means present state. Sometimes we call it current state. So if it's A, the output's forced to 0. So over here for the output, we're going to say 0, 0. If we're in B, the output, what'd you say?
It's 1 for C, right?
Yep. And then here's an X, or if we don't care. Now we're all done with this. Do you agree?
That makes sense.
Any questions?
I don't think so on that one. That was the state machines are I get the general gist of them. The only part that I'm having problems with is the diagrams of the A, B, and C's. I get everything else, like turning it into like a few K maps and finding Z and all that. It's literally just the state diagrams.
This part.
Yeah.
Okay, we'll make sure to touch on that. I think there's another question where they ask you to do a state diagram. All right, let's continue on. Any last questions here?
No, that made perfect sense.
All right, here it is. This is one that says draw a state diagram. So we'll get that done now. So it says consider the following code, which represents a synchronous Moore type state diagram. Draw the state diagram that this code represents. Label your outputs on the states and events on the edges. So here we can see that there's a parameter here. The parameter just means constant in Verilog. So we can see that we have a couple of constants. One of them is called A, and we defined it to be 0, 0. The other one is B, the other one is C, next one is D. So those must be the states. So the first thing we do is we draw in 4 bubbles, A, B, C, D, like that. Those are our states. And then we can see that for the registers, for the reg variables, there's a little y and there's a capital Y. So we can see down here on the rising edge of the clock, capital Y gets copied onto little y. So this is a flip-flop basically. Down here, right here, capital Y gets copied onto little y. So here's a register. Register just means a bunch of flip-flops in parallel. So here's capital Y and out comes little y. That's what this line over here is saying. On the positive edge of the clock.
So when the clock is 0 to 1, then it stores
yep. So when
is Y.
Exactly. So on the rising edge of the clock, little y copies whatever capital Y is.
Right.
Good. All right. So coming back here now, the case statement, we usually use those to implement the state transitions. So we can see, oh, how do the transitions work when we're in state A? So it says, oh, well, if the input W is equal to a 1, then the next state, so by the way, this here, the left side of the flip-flop is always what we call the next state, or NS. And then I think in your class they were calling this the present state, which
Yeah.
we usually call the current state. But anyway, this is saying if the current state, so that's little y, if the current state is A, well, if the input is 1, then the next state should be B. So we just draw that in. So it's saying, again, starting from A, if the input is 1, the next state should be B. So this is 1. Okay. And otherwise, it's saying next state should be C. So that's a 0. Make sense?
Yep.
Okay, so now we do the same thing for B. So it says, let's see, so we start from the B circle now, which is here. So if W is equal to 1, next state should be D. So we draw that, we put a 1 there. We should try to draw these, write these little transitions as close to the bubbles as possible, so we know, so we don't get lost later. And then it says, if W is not equal to 1, then the next state should be B. So it's saying if the input W is not equal to 1, so I should say 0 there, then it goes back to itself. Did that make sense to you?
Yep.
Okay, the next one is C.
And you just repeat this for the rest of the case statements, right?
Exactly. Do you want me to continue going through this, or you think you got it?
I think this one makes a lot of sense already.
Good. So now the only last thing to do is to see that there's also this reset. So if reset's ever asserted, see how if reset n is equal to 1, then we always make sure that the current state, so again, the present state is equal to A. So there's a reset signal that comes into here. And really, there are a bunch of resets that go into it. It doesn't matter what state you're currently in. If reset's ever asserted, the next state will always be state A, according to this, because this is an if statement. So it's, remember, if statements are prioritized. So if the top one has the highest priority. If reset is ever asserted, next state is always A. So notice that the picture got really cluttered just now. So the way we like to represent that is either by drawing a single arrow coming from out of space and just pointing at A, or we like to put a double circle around A, just to remind us that this is the reset state. Good?
Sounds good.
Okay, any questions before we move on?
That one made perfect sense.
Good. And one last thing here, actually, you can see that the output assignment, we didn't do that yet. So this is saying output is equal to 1 if the current state is equal to D. So in here, we can quickly just say, when we're in this state, output's equal to 1. And in all these other states, the output's equal to 0. Because in all these other states, they're not equal to D. Make sense?
Yep.
Okay, so now we'll move on. This says design a 2-level sum of products circuit such that the circuit will not exhibit a hazard. You only need to write down the final equation. Okay. Well, here's a K-map, and normally you could say that this satisfies the K-map. But the idea is, notice how there are a bunch of little islands here. So here there's a little gap. It's like a little river.
Yep.
We don't want those. We want it to be a contiguous. We want contiguous circles that cover everything with no gaps, and that's how you get rid of hazards. That's how you make a hazard-free circuit. So you do this sort of you circle in a way so that there's some overlap, and you see how now there are no gaps in between all the ones.
Right.
Okay, so now we generate an expression for that one. So that for that midterm there, we can see that A and B don't change. They're both zeros, and then D does not change. It's a 1. So that's the expression for that first one. Are you familiar with how to get these expressions?
Yeah. This was one that I understood a little bit more.
Okay. Do you want me to finish this, or should we move on?
You don't need to finish it, but I have a question about the don't care in there. Do you not need to include that as would including that be like just redundancy, or would that keep it from having a hazard?
This does nothing for us at all.
Okay.
This does nothing. It's a don't care. So we literally don't care about it. But for example, if that D were here, then we would love to take it into account. We would love to circle in a square. But that ultimately the 1s are our priority. if the D is somewhere over here and we would draw, if it would require us to draw another midterm here, that just makes our expression more complicated. There's no reason to do that. What we want to do is make sure we cover up all the ones. Again, the D is that we literally don't care. That's why we put a D there. As
Right.
long as all the ones, there are no islands and there are no gaps between them, then we're good.
That makes sense. I got you.
Okay, should we move on?
Yep.
All right, so here's Shannon's. It says apply Shannon's expansion to f with respect to y for the function below. So it's very similar to that first mux problem that we asked, that we looked at. That's why you asked me about it. It's saying that you're applying Shannon's expansion with respect to f, to expression f with respect to the variable y. So it's saying that y will be used as the select line to this mux. Shannon's expansion theorem just tells you that you can simplify any expression into some kind of multiplexer, right?
Right.
Okay, so the idea is if y is equal to 0, this input here that you hook up to the top input of the multiplexer, that should be the answer that comes out for f. So really this answer here should be where f of w of x, where y is equal to 0 and z. That's what you should pass into there. For the bottom part, it's f, w, x, and then where y is equal to 1 and z. So we want to evaluate this answer here and plug it to the top. And then we also want to evaluate the one on the bottom and plug it into the bottom input of the mux. Do you agree?
Right. That makes sense.
Okay. So this is very easy to do. Let's just plug and chug. So for the first one, it says where y is equal to 0. Well, that'll cancel out this term. It'll cancel out that term. The terms that remain are w naught z and wz. Remember, in this case, y naught would be equal to 1. So that there's a little bit of simplification there. See that?
Yep.
Good. And then for the bottom part, similarly now, y is equal to 1, making it so that this term cancels out. And I think that is the only term that cancels out. Do you agree?
Yep.
Okay. So what's left over is going to be x, y, z. And remember, we can plug in for y is equal to 1. So that's xz plus wz bar plus wz. Now we can simplify this a little bit. We can see on the top, we can pull out z, becomes w bar plus w. So that's going to become a 1. So that's going to be z ANDed with 1, which is just z. And then on the bottom, we can do something similar. We get xz plus w, pull out the w, z bar plus z. That becomes xz plus w. Do you agree?
Yep.
Okay, so we're just about done. We just figured out what the expressions are. So let's actually move this off to the side. So it doesn't bother us too much. So here they are. And we're going to grab these expressions. These are the things that we want to generate. Put that there. This is what goes to the bottom, and what goes to the top. Sorry, go ahead.
You just connect it to the inputs, like the w bar, or I mean the y bar is just going to be the z for the 0, and then when y is 1, it's just going to be xz plus w, right?
Exactly. So I think you got it from here. You can draw the circuit for this yourself, is what you're saying, right?
Yeah.
Good.
Yep.
Should we move on?
Yep.
Okay. This one says complete the truth table for the given circuit. So remember, this is a decoder, a 2 to 4 decoder. And what you'll notice is that one of the outputs is disconnected. And so when I look at this, we already know how the decoder works. It's supposed to be one hot. So the idea is if what we know for sure as well from doing the decoder upstairs when we did this earlier, if the enable is off, it'll force the output to be 0. So we can say, oh, well, here, 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 and here, the decoder is disabled, right? So we know that the output is going to be 0 in all those cases. And then what we do is we say, oh, well, now let's look at what W naught W1 is, which is hooked up to XY. So this one is saying 0, 0. So it's saying that the Y naught input should be asserted. Everything else would be zeros. So it'd be 1 orb with both 2 zeros. The answer is still going to be 1. So 1 goes there. So really we're looking at this, we're looking at this, we're looking at this, and we're looking at this. So this is saying that Y3 should be asserted. This is saying that Y2 should be asserted. This is saying Y1 should be asserted. This is saying Y0 should be asserted. So what we just saw is that y naught, if that's asserted, that'll get ORed. So the output's going to be f. If y1 is asserted, we can see here's y1. That gets certainly goes into the mux, into the OR gate. So the alpha would also be a 1. However, in this case, where we make y2 high, that's not connected to the OR gate. So actually, the output in this case is going to be a 0, because y naught, y1, y3, those are all zeros. So you OR them all together, you still get 0. In the final case where inputs are 1, 1, y3 is going to be equal to a 1. That goes into this OR gate. That's going to come out. So your output's going to be a 1. And now we're done. Make sense? All this stuff here?
Wait, could you repeat that last part again?
Yeah. I think you're probably focused on this part, why this is a 0, right?
No. I understand that. Y2 isn't connected to anything. But
okay. So you're asking about this. Why is this answer in the last row? Why is it a 1?
Yeah.
Okay. So it's saying that this device is enabled. So it depends on what xy is equal to. Xy goes into W naught W1 input. Oh, hang on a second. Just realized that this was reversed. All right, give me 1 second. We're going to redo this real quick. So it's good that you asked that. And you're going to get another chance to see it all right now. For now, let me delete this stuff. So you got to be, I got to be careful, I guess. So this X is W naught. This is W1. So for some reason they have the LSB on the left side, the MSB on the right, but this is still pointing at Y naught, right? We're looking at these numbers here. We're looking at that, looking at this, looking at this. So this one is still pointing at Y3. This one here is pointing at Y1. This is pointing at Y2. Right? You have to read it backwards. So this is the MSB, that's the LSB. So that gives you, when you look at that, and that becomes Y naught. It's telling you Y naught should be asserted. This one here, that's the MSB, which is a 1. LSB is a 0. So in binary, that's a 2. That's why I wrote Y2 here. Do you get that?
Yeah.
Good. And then similarly, there's Y1, there's Y3. An idea is, this is a simple problem. Ultimately, what we see is that Y2 is disconnected. So whenever Y2, we're trying to assert that, we know that the output is not gonna, like, it's not gonna be a 1, because none of these, it's always one hot. There's always one that's enabled, that's asserted at any given time. In all these other cases, why not? Well, we can see that why not, it certainly gets connected to the OR gate. And then if we look at Y1, that certainly gets connected to the OR gate as well. If we look at Y3, that certainly gets connected to the OR gate as well. So the idea is in each of those cases, answer is going to be 1. Because again, this is one hot, and each of those are connected. Y naught, Y2, and Y3. Sorry, Y naught, Y1, and Y3 are connected to the OR gate. See that?
Right. And then for like, so when W0 and W1 are both 1, then Y3 is 1, but everything else is 0, right?
Yep, Y3 is 1, everything else is 0. But that 1 that's on Y3, it gets hooked up to the OR gate. And if you OR anything with a 1, the output's going to be 1.
Right. Okay, I'm with you. That makes sense.
Good. Any questions on this?
Could you go over why it was reversed again, though? Why we have Y0, Y2, Y1?
Yeah. So if we look at this, see how X is hooked up to the LSB, Y naught, sorry, W naught. So it's kind of like this, right? So it's normally you write W1, W0 like this. And so in this table, they had it XY, right? So that, again, normally the way you specify which input it should be high should look like this in this order, but they have it in the reversed order. So I had to interpret the numbers backwards.
Okay. Oh, so really it's a 1, 0 for, okay. I see.
Yeah. So the idea is, for example, let's look at Y2, for example. So where X is equal to 0 and Y is equal to 1. So I'm literally just looking at this case here. Got it? So X is equal to 0, Y is equal to 1. So now I just map this, like I sort of think about this in the right way. So remember, W naught is equal to X, W1 is equal to Y, and I want to write stuff in the form of W1, W naught in my table. So I can see, oh, well, W1 is equal to Y is equal to 1. So W1 is equal to Y is equal to 1. So I put the 1 there. And then W naught, well, W naught I see is supposed to be X. X in this case I see is 0. So that 0 I'm going to put over here. And so now I'll interpret the number, and that's a 2. That's why I put a Y2 here instead of Y1. So normally you
Right.
read this, you might think, oh, that's a 1. But you have to remember that they tricked you in this question. They put this in the reverse order. That's really a Y2. Got it?
That makes sense.
Good. Any questions?
Nope, that makes perfect sense.
All right, moving on. It says, draw the logic diagram for a 4 to 2 encoder using any logic gates you want. Okay. So an encoder versus a decoder. You know what the difference is?
It makes it from 4 inputs to 2 inputs.
Yep. So let's draw this real quick. So this here, we'll call it A3, A2, A1, A0. And then we have 2 bits at the output. So we'll call it E1, E0. We'll just do a truth table real quick. Ultimately, this is simple. Once you get the truth table, you can synthesize sum of products expressions and generate a logic gate for each of those expressions. Do you agree?
Yep,
So we'll just do the truth table and we'll move on. Does that sound okay to you?
sounds fun.
Okay, so we have E1, E0. So it's very similar with 4 inputs. Let me actually just pull up the exact truth table definition. It'll be easier that way, so I don't have to write it all out. Let's close all other tabs, and then let's go to encoder truth table 4 to 2. And then here it is. We just copy that, and then now you'll know how the encoder works. See how it's 1 hot, just like we did earlier? It's basically the exact opposite of the decoder, right?
So you literally just reverse. Okay.
Yep. So remember, the decoder, what it does is you specify 2 inputs and it makes the output 1 hot. So literally the last problem that we did, again, like you specify which of the outputs should be high. So in this case, 0, 0, so it's specifying that that should be high. Now it's the other way around. You have 1 hot input, and then it tells you which state you're in. Good?
Yep.
All right. Nothing fancy there. So generally the idea is when you do a design that includes a decoder, you'll generally use an encoder as well, because they sort of come as a pair. That's what you just saw. And that like it makes it so that you don't have to use so many logic gates to set up your next state logic and so forth. But ultimately, again, in designs, when you use a decoder, a 2 to 4 decoder, you're probably going to use a 4 to 2 encoder as well, because they come as a pair. Fair?
Right.
Okay, moving on. Is it okay we move on?
Can we draw it with logic gates first before we?
Sure. So it's really easy. So for example, we look at A1, we can do a K-map, right? We see that A1 is 1 and 1 here. So what we do is we draw our K-map for this. So we do Y3, Y2, and then Y1, Y0. And then we know that with K-maps, we have to do gray code. So 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So here is the K-map. And we see that, so this is the K-map for A1, by the way. And we see that A1 is equal to 1 when Y3, Y2 is equal to 0, 1, and Y1, Y0 is equal to 0, 0. So we're looking in the first column, and we're looking at the second row. So there's a 1 over here. Do you agree?
Yep.
Okay, good. And then another one is at the final row down here. So it's saying same column, because Y1, Y0 is equal to 0, 0. So we're looking at this column here. And then now it's saying we're looking at the bottom row where it's 1, 0. So we put a 1 here. So in this case, the K-map doesn't help us, right? Because the largest circles we can draw look like this. So we'll just write the expression out for A1. So it'll be, let's see, Y3, Y2, Y1, Y0 plus Y3. This is the way I like to do it. I like to write the entire expression first, and then I like to put in the bars on top of it. So I see that there's a bar here, bar there, bar there. So I just put those bars in the same places for the first midterm. Now I do it for the other one. So I see, oh, there's a bar, bar, bar. So bar, bar, bar. And now we're done with the expression for A1. Do you agree?
Yep, that makes sense.
Okay, you want us to do it together for A naught too?
No, I know, I get what you're doing. But could you, like, for example, could you relate it to like, I don't know, I was looking at solutions before this just so I could get a good idea of what we were like going through and everything. I saw somebody had it as like they just on theirs they looked at the truth table and they were like A1 is 1 when like when Y2 is 1 and Y3 is 1. So could you just be like A1 equals Y2 Y3, or does that not work?
Let me see. So you said that they got a simpler expression compared to what we had over here.
Yeah.
Okay.
I mean, they didn't use any Boolean algebra or anything. They just looked at the truth table and were like, A1's 1 when Y2 is 1 and Y3 is 1.
Well, that's not the case from what we see here. But,
Or maybe Y2 or Y3 or something. It was something like along those lines.
okay.
Could you just say like A1 equals Y2 or Y2 or Y3?
I think you can from what I'm looking at. It looks like that would work. A1 is equal to Y3 ORed with Y2. That looks like it would work from right off the bat looking at this.
Gotcha. Okay. I was wondering if what they did was right or not after you went to the K map and I was like, oh no.
Hang on one second. I want to see why this is the case. Give me one sec. Hmm. Yeah, so this expression is saying that if y3 is ever equal to a 1, or if y2 is ever equal to a 1, then a1 is going to be asserted. I think that's a good choice. And I think that this is kind of this it's true. And I realize why the K-map didn't give us the same answer. And it's hard to see, but this is actually the naive answer. This expects that the inputs, these are the only combinations you would ever get for the input. But remember, with 4 inputs, you have additional combinations too, right? You
Right.
have like there are a total of 16. There are a whole bunch that are not listed. So again, this is kind of the naive solution. Where if you look at this table, yeah, it's true. A1 is equal to Y3 ORed with Y2. But remember, there are other combinations too. And in those combinations, like there might be cases, for example, where the inputs might be 1, 1, 1, 1. What are you going to do then, right? What should the output be then, right?
Right.
And the idea is with this expression, what it'll do is it's going to make it so that the output is 1. But maybe you don't want that. So really, if you want to be extra safe, you would use this expression up here. But however, if you're guaranteed that your inputs are 1 hot, which can be the case if you use an encoder, sorry, the decoder, right? This ensures that your outputs are 1 hot, except if the enable is asserted, sorry, if it's disabled, then the output's going to be 0.
Right.
But
Okay. I see what you're saying.
so again, this is true if the inputs are guaranteed to be 1 hot, meaning only one of them is high at any given time. But this is ultimately what we have here is still the like the de facto solution. This will always be true.
Right.
Fair?
That makes sense. Yep.
Good. All right. We good to move on?
Yep. Sounds good.
All right, this one says, name the device that is implemented by the following Verilog module. Be specific in your answer. All right. So we look here.
I think I said this was I mean, I ran through all of these, just getting like an answer for everything and making sure I had like a general idea of what stuff was. And I came out with, that this was a 4 to 2, a 4 to 2 encoder, but I wasn't 100% positive. So I wanted to run it with you.
It's called a priority encoder. So it's a here. Let me look. Let me give you a picture for it. So this is a priority encoder, and it has 4 inputs. And yes, it's definitely 4 to 2. You can see the output is 2 bits. And the key is that it's a priority encoder. So let me go to the images here really quick. So it's a 4-to-2 priority encoder, and I'll explain what that means in a little bit. Okay, these pictures don't do a good job of showing it. Let me write out what it means. But for now, you're right. It's a 4-to-2 encoder for sure. But there's an additional thing that we have to add there. The word priority.
Is that because
well,
Z1?
It's because there are all these don't cares here, for example. So this is saying if the MSB is 1, we're not even going to look at the bottom 3 bits. We're going to say that the answer is 3 right away. So this bit here, that MSB, literally is the most significant bit. It has the highest priority. And then what you see, if you go down by 1, if the highest priority guy is a 0, then we'll start looking at the next bit. And we see, oh, if this is a 1, that has the next highest priority. Then we don't even look at the bottom 2 bits. The answer is just going to be a 2. Make sense?
Okay, that makes perfect sense.
And then the idea is at the very end, this person has the least priority. That's why we check it last. And it's saying if everything before it is a 0, then we'll check this. And if this is a 1, then we'll make it so that y is equal to 0. But if none of these are 1, then it goes into this default state and it sends an x, which is a undefined or a contention value onto the output y. Ultimately, it's a priority encoder. Priority meaning that the MSB has the highest priority, LSB has the lowest priority. Good?
That makes perfect sense.
All right, shall we move on?
Go for it.
All right, you didn't have any other questions on this?
Oh, no, not on that one. That one makes sense.
Very good. This one says, consider the following block diagram of a 4-bit modulo 16 synchronous counter with a parallel load feature. Modify the diagram so the counter counts from 3 to 10 and then repeats. You want to go through this one together?
Oh, yes, please. I was so lost on this one.
Okay, let's read it one more time. It says, consider the following block diagram of a 4-bit modulo 16 synchronous counter. So modulo 16, like you can kind of ignore that if you want. The idea is that this is a counter. It's got 4 bits, so you can count between 0 and 15. So the idea is once you get to 15, it rolls over back to 0. That's what modulo means. If you ever like 16 mod some number, for example, the idea is like the counter once you get to 17, it's going to be 17 mod 16. So the answer will actually be a 1. The idea is once you get to 15, it'll roll around. That's all it means. Good.
Okay, that makes sense.
Okay, so it says consider the following block diagram of a 4-bit modulo 16 synchronous counter with a parallel load feature. Modify the diagram so that the counter counts from 3 to 10 and then repeats. So what we want to do is we want to make it so that we detect when we hit 10, and when we hit 10, we want to load a 3 into here so that it does not. So again, the full range of this is to go from 0 all the way to 15. We want to limit the range so it just counts between 3 and 10. Is that fair?
Yep, that makes sense.
Okay, so what we want to do is we want to check is the output, so is Q 3 down to 0, is it equal to 10? So this is a circuit, right? So here are the Q inputs. They go into the circuit, and then this will be a Boolean. It'll either be yes or no, right? You with me?
Yeah. Sorry.
Okay, and then here's a multiplexer, and I'm going to be a little lazy here. Here's the D input, and so the idea is there's a select line, and then what we do is we can load it with a 3. So in binary, a 3 is 0, 0, 1, 1, or we can load it with whatever the previous count is, and then we can hijack the input to the D. Hang on 1 second. Is that what we want to do? So we definitely have a clock. So let's draw the clock in real quick. And we actually don't need this feedback path because it's a counter. It has state already. So we don't need this mux at all. My bad. Get rid of that mux. These D inputs are just to load numbers in, to initialize the counter. So let's get rid of this, get rid of that. All right, and then get rid of this load here. So the idea is if we want a 1, 1 like that, in decimal, that's a 3. right? Because remember, they have the MSB on the bottom. So this has a weight of 1, this has a weight of 2. So 2 plus 1, that gives you 3. Do you agree?
Yep.
Okay, good. And so we're going to load a 3 into the counter if the current count value is equal to 10. So what we do, again, is we have this little detector here. Is the current count equal to 10? If so, on the next clock cycle, we're going to load in a 3. Does that make sense to you?
Kind of.
So again, the idea is this pattern here is eventually going to be a 10, which looks like this 1 0. Actually, I got to flip it around because they have it flipped. So it's 1 0 1 0. So that in binary, rather if you interpret it in decimal, that's a 10. So whenever we see this pattern here, what we're going to do is we're going to assert this load signal. We're going to make it high so that on the next rising edge of the clock, the 3 is going to make it onto the other side. So that basically it got up to 10. It counted up to 10. This realized that it's at 10. So what it does is it asserts the load so it ensures that the next value is a 3. So it jumps back to 3. And then the way that the counter works is it'll count all the way back up to 10. Once the 10 is detected, it'll load in the 3 again. It counts up to 10.
Logic.
Get it?
So the logic from the Qs would just be Q naught bar, Q1, Q2 bar, Q3, right?
Exactly. Okay. So this logic here is exactly what you just said. So this is 10. We'll give it a name. That was very good, by the way. Exactly what we wanted to hear. This is a 10 detected. And then it's exactly what you just said. So Q3, Q2, Q1, Q0, and then we put a bar on top of here and here, right?
Mm-hmm.
Simple. And do you see how that will ensure that you get a counter that keeps on looping between 3 and 10?
Right, that makes sense. But so you don't have to include any, so like for this problem, you wouldn't have to include any logic before that, like
Nope.
any logic for the Ds.
Nope. The 3, you're always gonna be loading back in a 3, right? That's always your starting value. So this is the initial value. They didn't write that here, but when you talk about a counter, this is just the initial value. It's the thing that you want to load it to. So you never have to change it. You just keep your initial value constant, unless for some reason you want it to count from 3 to 10, and then 4 to 10, and then 5 to 10. Then in that case, you would need to update what your initial value should be each time you hit 10, right?
That makes sense.
Good. Any other questions on this?
Nope.
All right, let's move on. Next one is 15. Consider a synchronous sequential circuit based on a Moore type machine that has a single input W and a single output Z, and it will detect a sequence of an on W of 1001, including overlapping sequences. When the sequence is identified, the output Z will be a 1, otherwise the output will be 0. So basically it's looking for this pattern of 1001. Once it's found that pattern, that it's going to assert the output and make it a 1, and then otherwise the output will be 0. For this problem, design a minimal state diagram finite state machine and fill in the Moore type state table provided. So to do these problems, you don't go to the table right away. You have to draw out a little state diagram to show how you would do this. So the idea again is we want to detect this pattern. So this 1001, 1001. Oops, I wrote 1000. So it should say 1001. So it's going in this direction into a detector. So the 1 goes into the detector, and then the 0 goes in, etc., etc. And the idea is by the time that all of these bits have gone in, the output of the detector should be 1, saying that, oh, we've detected this sequence. Is that fair?
Right.
Okay. So it's a detector, it's a sequence detector. The idea is the first bit that we want to check. So I'm going to call this B3. I'm going to call this B2, bit 1, and bit 0. I'm giving them names. Is that okay?
Yep.
So the idea is we have B3 equal to 1. That's one of our states. This is a weird name to give a state. We can call it state A later if we want, but for now it's more illustrative if we be a little more detailed in the name of the state for now. So first state is saying, oh, B3 was a 1. The next state is that B2 was a 0. Let's actually move this out of the way. Yeah, let's move it there. Okay. So B3 was a 1. B2 was a 0. The next one is B1 is a 0. The next one is B0 is a 0. So we have 4 states, but actually there's going to be one more state. We always have a reset state. And you saw that earlier too. Remember I drew the double circle?
Right.
Okay, so the idea is, say that the first number in, so remember the input is W. So the idea is if we detect a 1, then it means that, oh, we've detected this, right? So
Right.
again, when we come out of reset and we detect a 1, let me put a 1 here real quick. It means that we can transition to this state, meaning that so far within this pattern, we've detected the 1 over here, the B3.
That makes
Following?
sense.
Good. And then the idea is if we got a 0 from the reset state, then we'll just go back to the reset state because we can't advance at all. We have to get a 1. We have to get a 1. Otherwise, we can't advance through these this sequence here. So now we've finished drawing the transitions from the reset state. Let's focus on the B3 state. So for the B3 state, if it detects a 0, then let's move to the B2 equal to 0 state. So if it detects a 0, the idea is it can advance forward to this one. It means it's caught 2 of the numbers that are part of this sequence. But if it detects a 1, what it should do, if it detects a 1, it should just go back to itself. The idea is it cannot advance forward to this 0, but it's still caught a 1, so it can remain in this first highlighted state. Make sense?
Yep.
Okay, and now from the B2 state, so say that we were able to advance into the B2 state. Well, if the next number that we catch is a 0, then we can advance to the next state, which is saying that B1 is a 0. But if we don't catch a 0, meaning we catch a 1, then we're going to want to transition back to the previous state. The idea again is if we catch a 1, it's kind of like saying, oops, you didn't catch the 1001 pattern, but you did catch a 1, so you can start back here. You don't have to go back to the reset because again, you found a 1, so you can say that you've found B3 equal to 1. Make sense?
Yep.
Good. So now we're all done with B3 and B2. So we move on to the next state. So say that we've advanced all the way to B1 now. So now if we catch a 1, then we can transition to the final state. So this is saying that we found a 1. But if we found a 0, we're going to have to go all the way back to the starting point, back to the front of the line. The idea is, again, if you were to get to this state, it meant that you caught a 1, and then you caught a 0, and then you caught a 0. That's the only way you would get to this state. You have to catch a 1, then you have to catch a 0, then you have to catch another 0. That's the only way you can get to this state. So the idea is, if you were to catch another 0, well, you can't just restart at state B2, right? Because if you were to restart at state B2, it would have meant that the previous value you had was a 1, but it's not. The previous value was a 0. So you have to go all the way back to the start of the line. You have to try starting looking for B3 again, and then B2 equal to 0, et cetera, et cetera.
Okay, that makes sense.
Any questions?
No, that makes perfect sense.
Good. So the idea is you get close. Like this is so close to the promised land over here. But if you catch the wrong thing, you got to go all the way back to the beginning, all the way back to the start of the line. So now we're all done labeling for B1. So now let's do for the final state for B0. So now say we've made it to the promised land. We've detected the sequence. So that should actually say B0 is equal to 1, right? Because that's supposed to be the last bit. It was 1, 0, 0, 1. Yep. So now let's say that we're in the state where we say, oh, we've caught the final 1. Well, if you catch a 0 next, same thing, you're going to go all the way back to the front of the line. If you catch a 1, then you don't have to go all the way back to the front of the line, but you do need to leave this state. The idea is if you catch a 1, that's like saying that you've caught B3 equal to 1 now, right?
Right.
Good. And so now we've got the state transitions. We're all set here. We've got all our state transitions. What we can do is now we can also you can give these names. We'll call it state A, B, C, D. So those are the real state names because like you can't have an equal signs in the name of a state. But what we do know again is the output should only be 1 if we've caught the entire sequence of 1, 0, 0, 1. So that basically only when we're in only when we're in this final state should the output z be equal to 1. And all the other ones, z should be equal to 0. Do you agree? Because it means you haven't caught the full sequence yet.
Right.
Good. So now we have everything. I think that it says you do not need to do state assignments.
On the, and
Sorry.
then the table is just the table is just the same way. Your present state is just b0, b1, b2, b3, and then w equals 0 or just your sequences, and then z.
Exactly.
Yeah.
So yep. So just put A, B, C, D in here. Actually, there's also a reset. So there are a total of 5 states. So our reset, and then there's A, B, C, D. Or if you want, you can use the original names. You can call it B3, B2, B1, B0. But the idea is you can fill out this table pretty easily now by looking at this transition diagram. Do you agree?
Right.
And then what we also said, so let's just do one part so far, real quick. We know that the output should be 0 for all of them except for when the present state is D, meaning that you've caught the full sequence. Agree?
Yep.
Okay. You think you got this part on your own?
Yeah. Yeah. I think
Good.
I understand.
All right. Moving on. Actually, any questions before we move on?
Nope.
All right, next one says, consider the following state assigned table describing a state machine below. Find the minimal cost sum of product logic equations for the output, and next states.
We can skip this one.
Pretty easy, right?
Yeah.
Good. All right, this one here. What does it say?
Yeah, it doesn't have a title for the question. It's number 17, but I'm not sure. I think it wants us to circle the timing diagram or finish the timing diagram for D, E, F, and G.
Okay. Are there any gate delays we need to take into account, or are we assuming 0 gate delay?
I'm not exactly sure. I was wanting to talk to you about this one because I know that in our labs the inverters have like a 9 nanosecond delay from turning 0 to 1, and then like a 10 from turning 1 to 0. But I didn't know if.
Okay, let's do it the harder way. Let's assume that there are gate delays. You'll basically, it's the harder way because you'll learn more this way. You can do it the easy way, but if you do the hard way, you'll still learn everything you would the easy way, but you'll learn extra how to take into account gate delays. Okay.
Gotcha.
All right. So we're gonna assume unit gate delays, meaning, for example, let's do B first. Actually, let's look at D first. See how D is the inverted version of B.
Mm-hmm.
So what that means is normally, so first, let me just show you the easy path, meaning pretend that there are 0 gate delays. So let me just show you what that would look like first. So if there were 0 gate delays, D would literally just be whatever the inverted version of B is. So it gets inverted here, and then it gets inverted there, like that, right?
Yep.
So that's the easy way, and you could easily, I'm sure you could fill out the rest of this diagram that way. But we want to take into account the delays because that's what makes this problem challenging. So if there are delays, the idea is D doesn't actually invert till 1 unit delay later. So I'm going to assume that the distance between here, that's 1 gate delay, the distance between the vertical lines. So 1 gate delay, so you can see there's a 1 gate delay there. And then it stays low, then it goes high. So there's another gate delay. And then it stays high for the rest of the time. Good?
Yep.
Okay, so now we move on. Oops. Okay, the next one is E. The next one is E. And so it says that E is the output of this AND gate, which is ANDing D with A. So we're looking at D now, and we're ANDing it with A. So again, this is D, and then this is A. So we're ANDing those together. And we know that the AND gate, the idea is if either input is 0, the output's going to be 0, right?
Yep.
Okay, good. Let's get started. So here's E. We see that A is equal to 0 during this whole time. So we know E is going to be 0 for sure. And then the idea is A goes positive here, but D remains negative here. Or sorry, remains at 0. So the output's actually going to remain 0 too. The idea is, again, any input that's 0 is going to cause the output to be 0. So at this point, D goes high. A is also high over here. But remember, there's a gate delay, so you have to wait a little bit. So there's 1 gate delay. And then it remains high. Actually, it doesn't remain high forever because over here, A goes low. So there's a gate delay here, like that. And then there you can see that 1 gate delay. Make sense?
Yep, I got you.
This is easy, right?
Yeah, and then so you just go through the list for the rest F, G, H.
Yep. Do you think you got the rest, or you want to go through them
Yeah,
together?
I think I got that one. That
Okay.
makes sense. I just wanted to
Good.
talk to you about the delay part of it.
Okay. Did you have specific questions?
No. I just wanted to. I was just saying I wanted to go over it with you because I wasn't really sure on what it was,
Good.
but now
Good.
now I understand.
Good. So what would be interesting for you to do is fill out this chart once where you continue what we were doing with the gate delay of 1, and then do another chart where you assume 0 delay, and you'll see that the waves look completely different. As
Right.
ultimately as you make your way to H, see it goes through 1 gate, another gate, another gate, another gate. So if you look at the ideal scenario where there are 0 gate delays, which again we call it ideal because in real life that's not going to happen. You're going to see that there's a large difference between the H that you get in this plot and the one where you do it where 0 gate delays are present. Is that fair?
And so for H, it would just keep adding up. Like the gate delays would just keep adding up, right?
Yeah. So the idea is later, like you don't have to do any math on your own. The idea is first you generate what the plot of what F looks like. You generate a plot of what G looks like, and then you just focus on F and G, and then you make your plot just like we did just now with E. Is that
Right.
fair?
Yep, makes perfect sense.
All right. Should we move on?
Yep.
Okay. This one says for the circuit below, so this is a shift register with a load, it looks like. And it says if for the following sequence of events happen, first control and data are set to high, and then it's held that way for 2 clock cycles. And then the control is set to low, and data is remains high for 3 clock cycles. It's probably going to ask you what Q3, Q2, Q1, Q0 are. Yep. And it asks you to name the circuit. Shall we do this one?
Yep.
All right. So it's saying to begin with, control and data are set to 1. So remember that these multiplexers are ultimately here to hijack the path. Whenever we see multiplexers, we think, oh, something's getting hijacked. So the idea is it's the 1 input's going to make it through. Whatever is connected to the 1 input, it's going to ignore the 0 input to each of these muxes. It's the 1 input.
Right.
Exactly. The control is like a load. Remember how earlier we talked about the load, like to set an initial value. Good. So the idea is that this 0 here is going to make it to the input. This 0 will make it to the input. This 0 will make it to the input of the D flip flop. That 1 will make it into the input of the D flip flop. Is that fair?
Yep.
Okay. So it said this will be the case for 3 clock cycles. So let's start simulating this and seeing what happens. So let's just clean this up first before we start. So again, for the first clock cycle, all these values here, those will get loaded in. You agree?
Yep, that makes sense.
Okay. First, control and data are set high, held there for 2 clock cycles is what it says. So really, it's not really going to make a difference in the circuit. The idea is in the first, so here's the first clock cycle. The zeros, they get to make their way over like this, right? That's what it looks like. So everything was originally on the left side. So after the clock goes high, they make it onto the right side. Do you agree?
Yep.
Okay. But remember, on the next clock cycle, you're still loading in those same values. So it doesn't matter what the values were just now, because the idea is the multiplexer, the control line, you're going to override it anyway. So again, right now it's saying that control and data are both set high for 2 clock cycles. So on the second clock cycle, it's still going to look the exact same. So when the rising edge comes, that'll be these values here. That's what you'll see on that Q output of every single flip flop. Do you agree?
Yep.
Okay. So the idea is by the time that step 1 is complete, this is what it looks like on all of these. So now it says then control is set low. So now it's saying that we no longer want to hijack the path, but data remains high and is held there for 3 clock cycles. So data remains high and this is held this way for 3 clock cycles. So what that means is, well, that 1 that you see over there, that's gonna be waiting right here, right there. It's gonna wait to go into the flip flop, And so the first clock cycle comes along, everything shifts on over. So I gotta just fix this, move that one back a little bit. So that was the first clock cycle. You counting with me? That was number one.
Yeah.
And then let's do number two now. So number two comes along. It looks like this. Remember, all this time there's going to be another one that shifts in. Remember that this is held as a one, so a new one would have shifted in. So far we
Okay.
shifted twice. Did we shift once so far or twice?
This is the second one, I believe. Or wait,
Okay.
wait, wait. Actually, I'm not sure. You put the one in and then it came out, and but is that
Yeah, this is the second shift. That's why
Okay.
there are two ones in here. Yep. And then on the third shift, everything hops over again. And then a new one shifts in. And this should make sense too. The idea is if we're holding the data to high and we're not trying to hijack the path, then after 3 clock cycles, you would expect 3 ones to be in here for the leading 3 flip-flops. Do you agree?
right? That makes sense.
Yep. So now these 2 zeros, those got shifted out. They're no longer part of the circuit. So this is our final answer, 1110. Make sense?
Yep, that makes sense.
So Q3 is 1, Q2 is 1. Good. So it's 1110. And what you should have noticed is that pattern where I was taking everything and shifting it over. That's why we call this a shift register, because every clock cycle that comes by, everything advances forward by one register, by one flip flop. Good. So we call this a shift register.
And whatever value it's shifting is based on the data, right? The
Yep.
data and control.
Exactly. So if control is saying 0, it means we don't want to hijack the path. Then yes, it would depend on data. But if control is equal to 1, then it means we're gonna load whatever this initial value is. This is kind of the load value. Remember how earlier we talked about a load value? That's what this is. That's the load value. And in this control, we can actually rename that to load. So the name for this would be a shift register with load. Do you agree?
Would it be a 4-bit shift register with load?
Yep.
Like, is that,
Yep. If you want to.
That's what just I don't know, it just came to my mind. Like, I'm pretty sure we've done it in class.
Yep, a 4-bit shift register. That's a good, that's very descriptive, because there are 4 registers. Sorry, there are 4 flip-flops, meaning you can hold 4 bits. And then the way that it works is it shifts on each clock cycle. Good. Any other questions or comments on this one?
Nope, that's all good for that one.
Very good. We'll move on. This one is number 19. It says draw the Moore type state diagram for a counter circuit with 1 input W and 4 binary outputs B3, B2, B1, B0 that represent a binary count value. The counter counts up from 5 to 9 and then repeats. That looks really similar to a question that we did earlier, doesn't it? Where it goes from 3 to 10.
But we're doing 5 to 9 now.
Yep. And the other difference is that now instead of using a counter, we're doing a state machine for it. So there are 2 small differences, but ultimately it's still easy. This is really, really easy. This is saying going 5 to 9 and then repeat. So we know that if you want to represent numbers, so actually it tells us the state encoding should be 4 bits. So you know that with 4 bits, you can go from number 0000 all the way to 1111. So this here in decimal would be a 0. That there in decimal will be a 15. That's more than enough to capture this range. So we want to go from 5 to 9. So we can use the 4 bits to do that for us. So we can strategically design this counter. We can make it set the first state. So 5, by the way, in binary, that is 0, 1, 0, 1, right? And then the 9 is 1, 0, 0, 1. And so what we can do is we can start from 0, 1, 0, 1. The next one is 0, 1, 1, 0. Next one is 0, is 0, 1, 1, 1. 0, 1, 1, 1. Next one is 1, 0, 0, 0. Last one will be 1, 0, 0, 1. So make those the states like that. You can kill 2 birds with 1 stone. And then the idea is on every clock cycle, you just advance to the next state like that. And eventually it loops back around. And then the idea is you kill 2 birds with 1 stone because the state encoding is also what the output should be. Just literally whatever these 4 bits are, just route that to the output. And you're done with this counter. Easy?
I kind of understand what you're saying.
Okay.
But okay,
so
how would it work when it's so when it's 0, it's supposed to pause, right?
Oh yeah, you're right. So let me fix that. I didn't see that. So hang on 1 second. So this is 1, 1, 1, 1. And then if it continues to be 1, then it loops back around. But if it's 0, it's exactly what you just said. It just goes back, it retains the previous value. See that?
Gotcha.
Any other questions?
I don't think so. That makes sense.
Okay. So I think we're at the very end now. Question 20. Uh, any questions before we start question 20?
Nope.
All right, question 20, here we go. So it's asking you basically to make sure you know the differences between all these pictures here. So we can give all these names real quick. This one's
The
a
last
D
one's
latch.
D-latch, right? Yeah.
Yep, because it doesn't have the triangle. How about this one?
That's a D flip flop.
Yep, except see
D-
the bubble
D
there?
flop.
That'll tell you that it's a negative edge triggered flip flop. Good?
Okay, so then the first one is a positive edge triggered D flip. Or wait, no, that's a T flip flop.
Yep, so this is a regular T flip flop. Good. And so this is the question where we'll also talk about how to go from SR latch to D latch, because now you'll get a good sampling of all the types of latches and memory elements. This one's called a JK flip flop, but it's negative edge triggered. Again, you see the bubble there, it tells you it's negative edge. Okay.
Gotcha.
Alrighty. Get rid of that. All right. Negative edge flip flop. Okay. So I think you know how the D latch works. I think you know how the flip flop works and the negative edge flip flop. Again, negative edge just means we copy D onto Q when the clock goes from high to low. Fair?
Yeah, one is
Did you say something?
no, I said yeah, from 1 to 0.
Yep. Okay. We'll talk about, oh yeah, this is the negative edge JK flip flop. We'll talk about that last. The T flip flop's pretty easy. I'm going to show you how to go from a regular D flip flop to a T flip flop. T stands for toggle. So I'm going to draw out the architecture, and then later I'll do the same thing, how to convert from SR latch to a D latch. But first up will be conversion from a flip flop, from a DQ flip flop to a T flop. I'm being lazy, I'm not writing up flip flop. But the idea is the DQ flip flop symbol looks like this. DQ, there's the clock, here's the Q output, and we're going to put a little wrapper, kind of like when we write code. This is the main function in the big box, and then we call the DQ flip flop. It's a smaller thing inside. So the T stands for toggle again. So check it out. In this, the inputs to the T flip flop look like this. There's a T and there's a clock. So we have a clock input and we also have a T input. So that clock input will obviously connect to the clock input of the DQ flip flop. The toggle, what that'll do, so let me actually write it outside instead of inside. What that'll do is it'll control this multiplexer that goes in front of the D. So again, when you see multiplexer, you think hijack. So normally what should go into that path? And the way you answer that is you see what goes into the 0 input. So 0 is what, sorry, the Q normally goes into D.
So 0, it doesn't change state, and then
Yep. And then T, if T is equal to 1, it means we want to toggle. So we're going to literally invert whatever the previous value of Q was. And then we'll just feed it back into D. And that's why we call it a toggle flip flop. Make sense?
okay, so then if it's a so if T is 1, then Q bar is what's going into D, and then when T is 0, you just get Q, right?
Right, exactly. So that's exactly why we call it the toggle. If we want to toggle, then Q gets flipped on the next rising edge of the clock. If T is not 1, then Q remains the same on the next edge of the clock.
Okay, gotcha.
Is this picture descriptive enough?
Yeah, that makes sense.
Good. So now you know how the T flip flop works. So let's move that down. Next one is the JK flip flop. So remember how earlier we said with the SR flip flop or SR latch that there's this bad state that you want to avoid. Where was it? It's here, right? The idea is you don't want to both set and reset the output at the same time. Hang on, where was it? It was here. You don't want to both set and reset at the same time because it means you're trying to make it both a 1 and then a 0 at the same time. That's not good. So this is the bad state. So so people designed around the SR latch to make it so that we would be able, we would never be able to hit this state. Because again, this state kind of makes no sense where you try to both make it a 1 and a 0 at the same time. Is that fair?
Right. Yep.
Okay, so we come on down here. Here's the JK flip-flop. I'm gonna draw it out for you. So now J is analogous to the S, K is analogous to the R. So again, here's the truth table for the JK flip-flop. 0, 0, 0, 1, 1, 0, 1, 1. So again, what we said earlier was this was the state that we wanted to avoid for the SR flip-flop or the SR latch, because it doesn't make sense. This is the memory state where it takes the previous. This is where it makes it so that Q is equal to 1. This is where it makes it so that Q is equal, hang on a second, that one there is where it makes it so that Q is equal to 0. This is where it makes Q equal to 1. This is the one that we wanted to avoid previously, the one at the very bottom, right?
Yep.
Okay, so now what the JK flip-flop does is, okay, well, in this case, let's make it so that we do something useful here. Let's make it so that this one here gives you the inversion of whatever the previous value was. Get it?
Okay.
So I haven't shown you anything yet. I'm just describing how the JK works. Do you think that this is making sense so far?
Right. It makes sense.
Okay. So again, it's a modified SR flip-flop or SR latch. And the idea is these here look the exact same as the SR latch, SR flip-flop. The bottom one now, we're making it so that that's the reason why we changed these names, because S meant set, R stood for reset. Doesn't make sense to try to both set and reset it at the same time. So now we renamed it, we called it J and K. That these don't actually mean anything. The person who designed the JK flip-flop, I think his name was Jack Kilby, so he named it after himself, took his initials. So it doesn't mean anything. So it's a little harder for people to remember what JK does. But again, ultimately it's the SR flip-flop, but it overrides what the use is for that one bad case for the SR flip-flop. Is that good?
Gotcha. That makes sense.
So now we designed this, and this is designed pretty easily. We're going to go back to the DQ flip-flop. This is kind of the basic thing that we like as digital design engineers. We like the DQ flip-flop a lot. Going into the DQ flip-flop, what we're going to do is put a multiplexer there, just like we did for the toggle flip-flop. This time, this multiplexer is going to be a little bigger, so let's actually make it a little bigger. So here's the multiplexer. There it is. D goes in there. So, and then JK will control this flip-flop, sorry, this multiplexer here. So if JK is equal to 0, 0, if it's 0, 1, if it's 1, 0, if it's 1, 1. So we can see, oh, well, if JK is equal to 0, 0, then we want to take whatever the previous value of Q was. So what that means is we take Q, we wire that up right there. So now we've taken care of the first row. How about the second row? It's saying that if J and K are equal to 0, 1, then we want the next value of Q to be a 0. So here we tie that to a 0. So we tie that to ground on the breadboard. And the next one is here. It's saying that if J and K are 1, 0, then we want to make it so the next value of Q is going to be a 1. So we tie that to the red rail or VCC on the breadboard. And then in the final case, where J and K are equal to 1, 1, then we want the previous value of Q. So we take this, send it through an inverter, and that's what goes into this mux. And then the idea is on the next rising edge of the clock, whatever comes out of the multiplexer will become the new value of Q. Do you agree?
Right, that makes sense.
Does it seem easy how the JK flip-flop works?
Yeah, it's just based off of the SR latch, but with like a sort of like you don't have the bad state.
Exactly. So the idea is it's more well defined. The idea is instead of saying bad here, we say we're going to produce the inverted version of the previous value. Good.
Yep, that makes sense.
All right. So now you know how all of these things work. So at this point, here's a timing diagram. It says ignore gate delays. Do you feel like you'd be able to do this pretty easily, or do you want to do these together?
We only have 1 minute left. I don't want to keep you any longer, but if you feel it necessary, I'm not going to stop you if you want to go through it.
It's if you feel it necessary. How confident are you? I can spend another 10 minutes if you want. Do Would you like to go through this together, or do you feel confident in your ability to do this?
I'm kind of confident, but I'd like to go through it if we can.
All right, let's go through it. So let's start with P, and also after this, we're going to also talk about how to go from SR latch to D latch as promised. For now, we have the P. So P is the toggle. So we see that again, the input is W. So we're looking here. That's the toggle, and the previous value of P, as you can see, is low. So now we'll start drawing. So we see that at the first rising edge of the clock. So this is where we evaluate. So see how it's edge triggered. See that
Yep.
triangle symbol? It's saying only when there's a rising edge of the clock will P have an opportunity to change. Well, at this first rising edge of the clock, we do want to toggle. At the second, we don't. So see how before I actually do anything, I'm just seeing, do I toggle or not? So I look at what the value of W is, and I see, oh, well, at the first clock, I do want to toggle because W is high. So P goes high. And at the next clock, I don't want to toggle because W is low. Same thing for the next one. And up here, I do want to toggle because W there is high. Now I'm done for P. Do you agree?
That makes sense. Yeah.
Very, very good. So now let's get ready for the next one. So now we're going to look at R. That's the JK flip-flop. And the inputs are W and X. So just remember, this is kind of like the S. That's kind of like the R. Also, it's negative edge triggered. So now we look at the falling edge. So that's where we evaluate. So on the falling edge, this is a 1, that's a 0. This is a 0, that's a 1. That's a 0, that's a 0. That's a 0, and that's a 0. Everything look good to you?
Yep.
Okay, let's get started. So for R, let's see. R, again, it stays until the first falling edge. We make a decision. This is saying we want to set it, right? Because S is equal to 1, R is equal to 0. So we set it. And then here it's saying we want to reset it because R is equal to 1 here. So we reset it. Here it's the 0, 0 state. So it's saying we neither want to set nor reset, meaning it's the memory state. It stays the same. And then it does the memory state once more. That's what it looks like. Do you agree?
Gotcha. That makes sense.
Good. And now the next one. Next one is S, which is the DQ flip-flop. So they're very easy, just a sampling one. So same thing though, falling edge. So we look on the falling edge. So I'll just sample it visually first. So it's saying we're sampling X. So it's low over here. And then it goes high, and then it goes low, and then it stays low. So what happens is I sketch that out. So at the first falling edge, it's supposed to be low, so it stays low to the next falling edge. At this point, it goes high, so it stays high. And at the next falling edge, I see that it's low. And then here, at the next falling edge, I see that it stays low. So that's my final answer for S. Do you agree?
Gotcha. That makes sense.
Does it seem easy to you?
Yeah, I'm starting to get the gist of it. I think I'm starting to see a couple more patterns that I didn't before.
Good, good. All right, the last one is the D latch. So again, this one is just whenever the clock is high, X gets copied onto T. So now the idea is, again, during all the region that clock is high, whatever X is gets copied onto T. So here, when clock is high, right here, X gets copied onto T. So I make it look exactly like X. And then when clock is not high, this needs to stay the same. That value needs to stay the same. Clock is high again, so whatever. So the idea is this gets copied down, this gets copied down, that gets copied down, this gets copied down. So I can actually do that part first. See, I'm literally just copying those little pieces from above.
Mm-hmm.
And then the idea is all the segments in between, I just extend from the left. So I start from the left part, I extend outward. And then this one here, I start from the left, I extend outward. Same thing here, start from the left, extend outward, and now we're done.
Right, that makes sense.
And the way that I generated these, is it consistent with all the descriptions I've given for each of these?
Yep.
Good. Any questions before we move on to the SR latch, D latch stuff?
Nope, not so far. You've explained everything pretty well. Thank you,
Very
Richard.
good. All right, let's do the SR latch to D latch. So again, SR latch looks like this. 0, 0, 0, 1, 1, 0, 1, 1. This is the bad one. This is the Q prev. And then this is what we want Q to be 0. This one we want Q to be 1. Now let's compare that to the DQ flip-flop. Sorry, D latch. So D latch is very simple, so I'm not going to write it out. Excuse me. So what we see here for the SR latch, we already drew out what the SR latch looks like. So I'm just going to draw it as a box this time. Is that fair?
Yep, no worries.
Okay. So the idea is we want to wrap it up inside of a bigger box. We want this output Q to certainly come out as Q, and we have an input called D. This is the D latch now. So the idea is if D is equal to 1, well, we're going to put a multiplexer here. See how I keep hijacking these paths today? That's exactly how we want to think about stuff. We keep hijacking stuff with multiplexers. And then there's another multiplexer here as well. So this one goes into S, that one goes into R, and then the D input is going to select for both of these multiplexers. So there's 0, 1, 0, 1. So the idea is if D is equal to 0, we want Q to become what? 0, right?
Yeah.
So then again, we're looking at the 0 case. We want to reset it is essentially what we want to do. So we do this case. We make S equal to 0. We make R equal to 1. That'll make it so that we reset Q and force it to a 0. Make sense?
That makes sense.
And then if D is a 1, then what we want to do is we want to set Q and make it high. So again, if D is a 1, oops, let's come back down here. If D is a 1, then we want to make S 1, we want to make R 0. That's it. Now, there you have a D latch from the SR latch. Good?
That makes sense.
Good. You say that a lot. Does it actually make sense, or do you have any
Yeah,
questions for
no,
me?
actually, sorry, that's just a common term I usually say. No, it actually does make a lot of sense.
Okay. So we went over a lot of stuff. You've got to have a couple of questions.
Not exactly. I had a decent idea of like the general plan of like how to go about these problems. I just didn't exactly know the specifics, like some of the truth table things, and like for example on like on number 4, like I don't know, I knew what like an SR latch looked like, but it was just kind of like really good to go through it and like, say that set means make Q1, reset means make Q0, just some of these like smaller patterns that you don't really see.
Yeah, good. I'm glad. Do you feel more confident now that we've went through this exam?
I do for sure. Richard, you've
Good.
done an amazing job. Just wanted
Thank
to
you.
let you know.
Thank you. All right, last part, as promised, was the bubble pushing. Bubble pushing means that this picture on the top means if you ever drag that bubble to the left, then what'll happen is you get 2 bubbles that are on the left side now, but the body switches. The body of the gate, it used to be an or, but now it switches to an and. So this is De Morgan's law, the bubble pushing. So this is equivalent to the one on the right. Same thing, you can bubble push for this NAND gate. If you push the bubble to the left, 2 bubbles pop out. The body of the gate changes. So it was originally an and, it changes to an or. So you've got that. So there's some bubble stuff there. Sometimes they might say you have a bunch of and gates. They want you to convert it to a bunch of NAND gates. That's also easy to do. Oops. Say that they give you a circuit like this. They say convert this to a bunch of NAND gates. So what you'll do is you just put a bubble here real quick. Put a bubble here real quick as well. There you go. You have 2 NAND gates, but since you put bubbles there, you have to put a bubble on each of these paths too. 2 bubbles in a row means that you have 2 inverters in a row. So it's doing nothing, right? Means you haven't changed the circuit at all. Remember, the bubble is like an inverter, right?
Right.
Okay, so we have a NAND gate here, The trade-off is you have to put these bubbles on this side. Well, if we don't like this gate here because it looks funny, we can scroll back here and we can see, oh, well, this gate that's here, that's just a NOR gate. So then we can replace this with a NOR gate, and now everything is CMOS logic because everything's got a bubble in front of it.
Right.
Does that part make sense?
Everything makes sense.
All right, I think think we've gone through the parking lot questions. Any other last things you want to go over together?
I don't think so. I think you've explained everything thoroughly.
All right, I hope I hear good news about your exam tomorrow.
Hopefully, me too. Is there any way I can, you said you recorded the Zoom?
Yep, I'm gonna send it over to you. I might have to like upload it somewhere because it's gonna probably take like 30 minutes because it's like a 2-hour recording. I'll upload it and I'll share a link with you. Okay.
Awesome. Thank you so much, Richard. I appreciate it.
Sure. Yeah, good luck
And,
tomorrow.
do I need to do anything before we leave, like for the payment, or does it just automatically?
It'll be automatic.
Okay, awesome. Well, thank you
Alright.
so much, Richard. I appreciate everything. Hopefully I will do good on this exam. I'm hoping for it. But
Yeah, I
anyways,
want to
but
hear
thank
good
you.
news. All right.
Have a good
Good
night.
luck tomorrow. You too.